Right now, every human being, every piece of history, and every living ecosystem we know of is confined to one fragile sphere. We are entirely bound to Earth, suspended in a cold, silent void. That absolute isolation creates a mathematical vulnerability. To guarantee our long-term survival against cosmic or self-inflicted extinction events, we have to establish a foothold on another world. That brings us to Mars. Picture a sprawling, active city operating under a dusty pink twilight, with the towering peaks of Olympus Mons looming in the distance. Is setting up a permanent colony on this neighboring rock an achievable goal, or is it a lethal illusion that will drain our resources? Securing our future relies entirely on finding a viable secondary ecosystem. Bridging the gap between terrestrial life and the Martian environment has become the definitive test of our species' longevity. When evaluating the hundreds of moons and planets in our solar system, researchers focus entirely on specific, uniquely compatible metrics. Comparing this side-by-side model, a Martian sol is 24 hours and 39 minutes, perfectly matching human circadian rhythms. Their axial tilts are nearly identical, Earth at 23.5 degrees, Mars at 25, creating familiar seasons. Subterranean cross-sections reveal massive deposits of frozen water at the poles. This ice acts as the absolute prerequisite for any permanent settlement. We can melt it for hydration, separate it into oxygen for breathing, and synthesize it into rocket fuel. A 24-hour rotation, seasonal shifts, and accessible water. These three metrics isolate Mars as the only mathematically viable candidate for a second Earth. From orbit, the red planet appears serene, but the moment boots touch the regolith, astronauts face a brutal, unforgiving crucible. This chart tracks atmospheric pressure. Earth's thick atmosphere provides a comfortable baseline, but the curve plunges dramatically for Mars. Its atmosphere is barely 1% as dense as ours, and it is made almost entirely of carbon dioxide. Without a thick atmosphere to trap heat, the planet experiences violent temperature swings. As you can see on this overlay, while daytime highs can reach a mild 70 degrees Fahrenheit, nighttime temperatures frequently plummet below -100 degrees. This cross-section shows the invisible, persistent threat. Lacking a protective magnetic field, the surface is constantly bombarded by cosmic rays and solar flares that slice right through the thin air. Exposing a human body to these conditions without heavy, technological shielding is instantly fatal. The transit to Mars remains a monumental engineering challenge, but the ultimate hurdle is the long-term preservation of human life within a freezing, irradiated vacuum. To bridge the gap between human biology and a lethal environment, aerospace engineers are executing a rigid technological roadmap. Phase 1 relies entirely on autonomous systems. Long before a crew launches, heavy robotic rovers will land on the surface, prep the terrain, and synthesize stockpiles of oxygen and fuel. Once the crew arrives, their primary defense will be next-generation spacesuits, wearable life support systems engineered to regulate core temperatures while blocking lethal doses of radiation. This architectural cross-section reveals the design of the primary settlements. Notice how the multi-level living quarters are enclosed and pressurized, physically linked by subterranean tunnels to minimize surface exposure. Food supplies will be cultivated inside transparent greenhouse domes, initiating a sustainable, closed-loop ecosystem that recycles both air and water. We cannot wait thousands of years to biologically adapt to Mars. We have to master the engineering of artificial environments to adapt Mars to us. Fast forward a few decades, and those isolated outposts will expand into a thriving, permanent settlement, operating seamlessly in the harsh environment. Maintaining an ecosystem of that scale requires the combined output of global aerospace agencies, rapid iterations in material science, and human courage. True mastery of the Red Planet requires completing the return trip. We have to successfully launch a fully fueled, crewed vehicle from the Martian surface and navigate it safely back to Earth. Every rover currently drilling into the regolith and every satellite mapping the polar ice is gathering the raw data needed to write the blueprints for those future vehicles and cities. Mars serves as the ultimate proving ground to ensure human civilization survives a single planetary disaster. While a self-sustaining Martian city remains a project of the future, the ongoing development of these life support and propulsion systems ensures that humanity is no longer confined to a single world. Mars today is a frozen, silent desert. It is a landscape defined by freezing temperatures and endless stretches of dry, red dust. But that barren surface is actually a record of a more active past. Beneath the craters and dunes lies a planetary graveyard. Geological evidence points to a world that once held vast, deep oceans, leaving a massive gap between its watery origin and its current state. We have to look back 4.6 billion years into the era when the planet was first taking shape. The dry landscape we observe today stands at the end of a long timeline that began in a cloud of dust. At the center of the early solar system, our newborn sun was surrounded by a violently swirling solar nebula. The space surrounding the sun was empty. Mars did not exist yet, leaving only billions of microscopic particles of rock and dust floating in the void. Through accretion, gravity acted on this dust, clumping together individual particles until they collided and stuck. This gravity created an escalating cycle. Small clusters became boulders, and those boulders eventually merged into a single, massive protoplanet. These continuous impacts were violent. The kinetic energy of rocks constantly smashing together generated immense, unrelenting heat. The resulting young Mars was a glowing sphere, composed entirely of molten magma. A continuous bombardment of ancient asteroids from the surrounding debris field kept its surface in a liquid state. The cold rock we know today began as a chaotic ocean of fire, shaped by the mechanics of gravity. Directly above this molten surface, the young planet possessed no sky. It was exposed to the cold vacuum of space. This satellite image shows an ancient volcanic caldera. Eruptions of this magnitude drove a process called outgassing, releasing trapped gases from deep inside the Martian mantle. Over millions of years, these relentless eruptions pumped enough gas to form the planet's first thick atmosphere. This newly formed sky trapped heat, which allowed the molten surface below to finally cool and solidify. As temperatures dropped, water vapor in the atmosphere began to condense, triggering the planet's first massive, sustained rainstorms. Deep valleys once held rushing rivers that carved through the rock, long before the planet lost its surface water. During this period, Mars was warm and wet, possessing a climate that mirrored the early days of Earth. The planet's destructive volcanic forces were the exact mechanisms that engineered this stable, watery world. This stable, wet period of Martian history eventually ended. Mars began to lose its protective atmosphere as the gases were stripped away and lost to space. Without atmospheric pressure to insulate the planet, liquid water could no longer remain on the surface. Rivers turned to dry dust, and lakes vanished as the surface water evaporated into the thinning Martian sky. Powerful cosmic winds then began to sweep across the newly unprotected surface, scouring the landscape. Scientists are still piecing together exactly what stripped the planet of its protective gases and left the surface exposed. That collapse brings us to the present day and the cold, red desert we observe through our telescopes. In a single cosmic cycle, Mars transformed from a sphere of molten fire to a world of flowing water, and finally to ice. The barren surface is a frozen time capsule, preserving the skeleton of a once active world. If there was once a stable climate and liquid oceans, it is possible that life evolved before the atmosphere vanished. We must now search the ancient riverbeds for traces of biology, the focus of our next chapter. Are we alone in the universe? It is the oldest question we have, and to find the answer, we have to look outward. Look at the surface of Mars today. It is a freezing, irradiated, and desolate wasteland of dust and stone. Scan the horizon, and you won't find a single blade of grass, a drop of liquid water, or any visible sign of biological activity. But planetary models and geological data point to a paradox. The frozen desert we see today is hiding the remnants of a very different world. 4 billion years ago, a much thicker atmosphere trapped heat against the surface, allowing massive amounts of liquid water to flow freely across the planet. We are talking about winding river networks, massive floodplains, and deep lakes that mirrored the early environments of Earth. Because those oceans dried up billions of years ago, we aren't sending probes to hunt for living, breathing creatures. We are searching for the microscopic chemical remnants they might have left behind. Proving that a dead planet once hosted life requires analyzing the geological record with extreme precision, as these rocks contain the only surviving data from that era. The Perseverance rover is currently operating on the surface, equipped with the most advanced suite of geological sensors ever sent to another world. Mars covers 144 million square kilometers of surface area. Finding microscopic traces on that scale requires targeting a location with the highest probability of preservation. Researchers identified Jezero Crater, a massive impact basin, as a primary target because orbital data indicates it was once an ancient, standing body of water. This false color orbital scan reveals a massive branching delta spilling into the crater. These structures form when a river slows down, depositing silt and clay into a standing lake. The ancient river channel's path remains clearly visible today, flowing straight down into the basin. Because deltas trap and pile up layers of fine sediment over millions of years, this specific deposit is the most logical place in the solar system to look for buried biological signatures. Now that we have the macrogeography mapped out, the rover must investigate the microscopic composition of the sediment layers themselves. We aren't going to find complex fossils compressed in these rocks. Microbes were likely the only form of life that ever had enough time to evolve here. Instead, we search for biochemical anomalies left by microscopic life. Normal rocks form with predictable, repeating mineral structures, but rocks that hosted biology contain concentrated carbon-based molecules or microscopic textures produced only by living organisms. To isolate that evidence, Perseverance approaches targeted rocks and uses a specialized mechanical drill to carve out exact cylindrical core samples. Once a sample is extracted, the rover seals it inside a sterile titanium tube and carefully stores it on the Martian surface. Every one of those sealed tubes operates as a pristine time capsule, locking away the chemistry of a habitable era before surface radiation can degrade it. As of today, the objective reality is that the rover has not yet found any confirmed evidence of past or present life. But a rover is limited. It cannot carry the massive, highly sensitive laboratory equipment required to prove definitively that a microscopic chemical anomaly was created by biology. That kind of proof requires the full weight of a global scientific community, using electron microscopes and mass spectrometers in laboratories on Earth. To get those samples into human hands, space agencies are currently designing the Mars Sample Return mission. This mission will require an unprecedented mechanical feat: landing a retrieval vehicle, loading the titanium tubes, and firing a rocket directly off the Martian surface to carry the payload into orbit. The definitive answer to whether biology exists beyond Earth is currently sitting in the Martian dust, waiting for a ride home. While we wait to analyze the chemistry of the ancient past, our next chapter explores the towering giants of the present, the massive peak of Olympus Mons, and the vast chasm of Valles Marineris. Even as we dig for the smallest traces of history, the colossal geography of Mars still commands our awe. For humans, Mount Everest is the ultimate benchmark of scale. Rising 8,848 meters above sea level, it represents the jagged limit of what Earth's shifting tectonic plates and gravity can produce. We find a similar extreme in the Grand Canyon. It is a mile-deep trench carved into the crust over millions of years by the persistent flow of water. Given these terrestrial limits, we might expect a smaller planet to have smaller features. Mars is roughly half the diameter of Earth, with significantly less surface area to work with. Yet this smaller world contains both the largest volcano and the longest canyon system ever discovered in the solar system. It seems a contradiction. A planet with a fraction of Earth's mass has somehow managed to construct geological features that make our own mountains and canyons look like foothills. Understanding these Martian giants requires looking past our experience on Earth. Their scale is the direct result of a specific environmental balance, lower gravitational pull, and a stationary crust. Olympus Mons is the peak of that balance. Its summit rises 22 kilometers above the surrounding Martian plains. When compared side by side, the scale is difficult to process. Olympus Mons is nearly 3 times taller than Mount Everest. On Earth, the crust is divided into moving tectonic plates. As a plate slides over a stationary magma hotspot, it creates a chain of smaller, separate volcanoes, like the Hawaiian Islands. Mars operates differently. The Martian crust is a single solid shell that does not move. When a hotspot formed under Olympus Mons, the crust stayed locked in place. Because the ground never shifted, every eruption over billions of years deposited lava in the exact same spot, allowing the mountain to grow outward and upward. Mars' lower gravity provided the final condition for this growth. With only 38% of Earth's pole, the Martian crust could support the weight of a 22-kilometer mountain without the base buckling or sinking into the mantle. Olympus Mons is the record of a volcanic engine that never moved, pumping lava into a sky that offered very little resistance. While Olympus Mons grew upward, the planet's surface was also being pulled apart. Valles Marineris is a canyon system 4,000 kilometers long, stretching the distance from New York City to Los Angeles. Unlike the canyons on Earth, this 7-kilometer deep abyss was not primarily formed by the erosion of water. Its origin is tied to the volcanoes themselves. As the massive Tharsis regions swelled with lava, the weight of those volcanoes put immense mechanical stress on the surrounding crust. The surface eventually reached its breaking point. This was a tectonic crack on a planetary scale, where the crust literally pulled itself apart. As the surface stretched, massive blocks of the crust dropped downward, creating the vertical 7-kilometer cliffs that define the canyon today. Valles Marineris is a massive geological scar, a permanent record of the time the Martian crust buckled under the weight of its own volcanoes. Because Mars lacks the rain, oceans, and plate tectonics that constantly reshape the Earth, it has no way to recycle its surface. These enormous features are perfectly preserved. They offer a direct look at the violent volcanic and tectonic forces that were active billions of years ago. These are the landmarks that future explorers will use to navigate the planet. Standing on the edge of Valles Marineris, they will be looking at a canyon that could fit the entire United States inside it. Mars shows us that a planet doesn't need to be large to produce massive wonders. By studying these giants, we are finally piecing together how a world half the size of Earth managed to build the most imposing landscapes in our solar system. For generations, humans have looked up at the night sky and imagined a future where we live across multiple worlds. Out of all the planets and moons orbiting our sun, Mars presents the most realistic target for humanity's first permanent settlement. This ambition is a direct continuation of the path we have been on for decades. We have already taken our first steps on another celestial body, proving that we can navigate and operate in the vacuum of space. But planting a flag on the moon for a few days is entirely different from sustaining a civilization. Mars is one of the most hostile environments we have ever encountered. To simply stand on its surface without immediate, massive engineering support is a guaranteed death sentence. This satellite photograph reveals the stark reality of the Martian surface. It is a desolate, cratered volcanic landscape, completely devoid of the natural resources we require to live. The atmosphere is composed of more than 95% carbon dioxide, rendering it entirely unbreathable. The planet is also frequently swallowed by violent, massive dust storms that completely block out incoming sunlight. When the skies are clear, that thin atmosphere offers virtually no heat retention. Average temperatures plummet to -63 degrees Celsius. Then there is the invisible threat. Earth's magnetic field protects us from deep space, but Mars lacks this planetary shield, resulting in cosmic rays and solar radiation directly bombarding the planet. Over a very short period of time, continuous exposure to this unshielded radiation actively degrades human cellular structures and DNA. Standard spacesuits cannot block this long-term damage. Surviving here requires the construction of an entirely artificial, technologically flawless ecosystem. Before anyone can build that ecosystem, we have to solve a massive logistical hurdle, transporting heavy infrastructure across tens of millions of miles of deep space. Engineers worldwide are developing heavy lift vehicles that can generate the sheer thrust required to push interplanetary payloads out of Earth's gravity well. Even with heavy transport secured, humans cannot assemble the initial base themselves. An autonomous robotic vanguard must be sent first to establish a working power grid. We already have the capacity to operate complex machinery on the Martian surface. As this rover photograph demonstrates, our robotic foothold is well established. Future automated machines will need to drill into the surface and process materials, and set up extensive solar farms long before a human crew ever leaves the launch pad. Completing this transport and setup phase autonomously is the only mathematical way to ensure the first human explorers do not arrive to a powerless, freezing trap. Once a reliable power grid is running, the next immediate problem is shelter. Traditional above-ground structures offer practically no defense against the constant barrage of cosmic radiation. The first explorers might rely on highly pressurized inflatable surface modules for their initial short-term stays. But to achieve a permanent, colonizable settlement, the primary engineering solution is to abandon the surface entirely and build deep underground. Burying habitats under several meters of dirt creates a dense physical barrier. This soil substitutes Earth's missing magnetic shield, absorbing incoming radiation. It also works as a powerful insulator, shielding the habitat from freezing surface temperatures and keeping the interior completely stable. By digging into the planet's own crust, engineers can turn Mars's harsh geology into our primary survival tool. With shelter and power secured, the final immediate threats are the absolute lack of breathable oxygen and the absence of fertile soil for food. To counter this, settlements will rely on closed-loop life support systems. In an environment this hostile, absolutely no resource can be wasted or thrown away. This photograph of the International Space Station illustrates our primary testbed for closed-loop survival. Crews have spent decades perfecting these exact recycling systems for Mars. On the ground, heavily pressurized greenhouses will be engineered to extract carbon dioxide directly from the Martian atmosphere and convert it into breathable oxygen. Liquids will be managed with meticulous precision. Every drop of moisture inside the base, from ambient humidity to human sweat, will be continuously captured, purified, and routed back to the water supply. True planetary colonization means engineering a flawless, self-sustaining biosphere. Survival ultimately relies on maintaining a perfect chemical balance. Right now, inside clean rooms and assembly facilities across Earth, thousands of engineers are building the infrastructure required to bridge the gap between our worlds. This modern international push relies on the exact same methods we used decades ago in mission control, solving seemingly impossible aerospace challenges through iterative testing, rigorous data analysis, and mathematics. Every failed engine test, every successful launch, and every byte of telemetry sent back from a robotic rover builds the specific technical framework required to sustain a human presence on the Martian surface. Mars is the ultimate test of human engineering, representing our collective drive to function and thrive in an environment where every single breath and calorie must be manufactured from scratch. This global effort is already in motion, turning the massive logistical barriers of interplanetary travel into a series of documented, solved engineering problems. After decades of orbital math and millions of miles in transit, a human boot finally meets red soil. A successful landing requires millions of individual components, from radiation shielding to supersonic parachutes, to function in a sequence where a single millisecond of lag results in total loss. It is the most complex mechanical undertaking in history. But the moment the dust settles, the scale of the isolation sets in. Looking up into the Martian sky, Earth is nothing more than a tiny, pale blue speck fading into the blackness. The months spent crossing the vacuum were a feat of navigation. Now the focus shifts to the biology of the people left behind on the surface. Outside the pressurized walls of that landing vessel is an environment that cannot support human life. Looking closely at the edge of the planet, you can see the immediate problem. Mars has an atmosphere roughly 100 times thinner than Earth's, composed almost entirely of carbon dioxide. There is zero breathable oxygen. Below that thin layer of gas, surface temperatures frequently plummet to -100 degrees Fahrenheit. The planet also lacks a global magnetic field, leaving the rocky crust completely exposed to lethal cosmic radiation. If a crew intends to stay, They have to figure out how to manufacture every single resource they used to get for free on Earth, entirely from scratch on a frozen desert. Lasting 24 hours on this surface requires an airtight chain of mechanical solutions, where any leak or power failure is fatal. Heavy lifting has to start years before a human crew ever leaves the launch pad. Robotic explorers arrive first. Fleets of autonomous machines will need to grade the crater terrain, lay foundations, and assemble modular, pressurized shelters piece by piece. To pull this off, engineers plan to use in situ resource utilization. This means scooping up raw Martian dirt and baking it into reinforced building materials right there on the surface. There is no alternative. Shipping massive steel structures across the solar system requires far too much rocket fuel to be practical. Processing those local rocks and powering the initial robotic fleet demands massive amounts of electricity. Early missions will rely heavily on sprawling solar arrays deployed directly onto the dirt, capturing sunlight during the day. Harvesting local materials and capturing light are the prerequisites for establishing a permanent foothold. Once the pressurized walls are up and the power is running, the biological reality sets in. A crew needs clean air, drinkable water, and a steady stream of calories. Inside the habitat, closed-loop life support systems must operate without interruption. Every exhale, every drop of sweat, and all wastewater must be captured, purified, and recycled back into the drinking supply. Because the native Martian soil contains toxic perchlorates, astronauts cannot plant seeds in the ground. They will cultivate crops in hydroponic greenhouses, growing their food entirely under artificial lighting. On the left, surface features are clearly visible during a calm period, when the base functions smoothly. But massive dust storms can envelop the globe, choking out the sun for months and threatening the solar grids keeping habitats warm. If the power grid drops and the water filtration halts, there is no resupply ship waiting in orbit. A failure in the life support machinery is immediate. Keeping a small team of researchers alive for a year is one thing. Sustaining a massive, permanent city requires a different scale of engineering. A population of thousands needs industrial power plants, heavy transportation networks, and millions of calories in agricultural output every single day. Then there is the medical toll. Residents would live their entire lives indoors, constantly shielded from radiation, isolated from everyone they have ever known on Earth by a multi-month transit window. To prevent a colony of that size from collapsing, we still need significant technological leaps in heavy infrastructure and long-term human medicine. Scaling to this level forces a transition from aerospace engineering to civil governance, requiring a stable, self-contained society that can function without a supply line from Earth. Mars will never offer humans a blue sky, open oceans, or a gentle breeze. Billions of years ago, liquid water did carve these winding channels into the rock, but that world is gone. Today, the surface is permanently arid and frozen. Anyone who goes there will spend their days behind reinforced glass and heavily shielded walls, strictly adhering to survival protocols just to make it to tomorrow. Its value to us now is as a rugged, uncompromising laboratory. It is a destination for rigorous scientific exploration. Treating Mars as an easy backup plan ignores the staggering, permanent lethality of the planet. Despite every obstacle, establishing a foothold on that planet remains our greatest test. Pulling it off will require generations of technological invention and international cooperation. It pushes our engineering limits and tests our collective willpower against a hostile environment, and it is only the first step. Surviving Mars gives us the tools and heavy lifters we need to push deeper into the void. Just beyond the asteroid belt, the most massive planet in our solar system is waiting. Next time, we head to Jupiter.